So this is just a quick demo of a piece of code that I wrote, which generates spatially oriented level diagrams. I wrote it as a plugin for ASE GUI, and ASE is the Atomic Simulation Environment, which is a Python set of modules in which you can interface with electronic structure codes. It has a GUI which you can use to visualize XYZ files as well as a bunch of other file formats. And there are also other functions within it. And so I wrote a plugin to use the molecular visualizer. So in this directory here, I have 3 files. I have a Gaussian formatted checkpoint file. I have a Gaussian output file from a relaxation, and I have the relaxed geometry. This is just for lithium hydride, but you can do it for any arbitrary molecule. So I'm going to call up the ASE GUI by doing ASE-GUI, and I'm going to give it the XYZ file so that I can visualize it. And so here, if I use the right mouse, if I right click, I can rotate. If I use the scroll wheel, I can zoom in and out. And so to use the actual sold plugin, I go to Tools, and I go Sold, and another window will pop up. So here, I just follow the instructions. I can choose a Gaussian output file. I can choose the formatted checkpoint file. I'll choose the number of occupied states I want to do the level diagram, or I want in my level diagram. So I'm going to choose 1. I'm going to choose the number of unoccupied states. I'm going to choose 5. The number of bins should always be around 100, which I've set as the default. So for these spatially oriented level diagrams, I'm not just plotting the orbitals in terms of energy. I'm plotting them in terms of, I'm making areas with more weight on the wave function darker and areas with less weight lighter. So I can integrate along some arbitrary axis. And the way to choose that arbitrary axis is to choose 2 points within the molecules. So I'm going to choose hydrogen and lithium. But for molecules with more than 2 atoms, you can choose like any 2 arbitrary atoms. To select those points, I just hold Control and click the 2 atoms and hit Confirm. And the scaling method, so to determine like the color, I basically scale the value of the integrated wave function along that axis. And so there's 2 ways you can do that. You can do that scaling globally over the set of orbitals that you've chosen. So the 6 states here, where you can do it on a per orbital basis, which yields more resolution, but you can't directly compare the 2. So if I click Run, the first time takes a little longer because it has to generate cube files. But after this, you can tweak parameters, and it won't regenerate the cube files. So subsequent runs will take less time. Luckily, it's a small molecule, so generating the cube files doesn't take too long. And so right now, it's just running in the background, integrating the wave function along the axis between these 2 points. And after that's done, a window will pop up with the level diagram. So here, it's a couple things. So this is a sort of simplified graph. It also writes out a data file if you want to do more in-depth plotting. I find it's useful to put the edges of the box. So you can put those as dashed lines vertical, or putting the positions of atoms. So like where the hydrogen is about here and the lithium is about here. And so here we can see there's different areas of weight on the wave function. So here is on the hydrogen atom, and here there's sort of this gap. So there's a fair bit of weight in this area and in this area, but nothing in between. So this is with the global scaling. I can do this additionally with per orbital scaling. So if I just close that and click orbital and rerun it, it will recalculate, and a new window will pop up. And so you can see that there's sort of more resolution within each orbital, but it's harder to directly compare between orbitals because they're scaled at different values. So this is done just using matplotlib, and so you can save the figure as a ping or an SVG file, so in vector format. Additionally, so there's a few files that get written out. So if I just close this and look at what is popped up in this directory, so I can see the cube files for the orbitals that I wanted. Atom projections gives the coordinates of the atoms projected onto the vector that you've specified. So you can use that to see where atom positions are relative to this arbitrary vector. This is just the configuration file used to feed into C++ code, which is on the back end. The projected sums contains all the data that's used to plot, so you can use a plotting script, which you can find on my GitHub in the sold directory. And then you can do sort of more advanced options with that, like the vertical lines or things like that. I found that that's useful. So when you run the plugin initially, you can sort of get an idea of what it's going to look like, and then you can do better quality plots playing with those plotting parameters. So that's just a quick demo. You can find this on GitHub under github.com/gclen or gclen/sold. There's some documentation there. So here there's test cases and a better comparison to the bubble diagram, so you can sort of see how everything works.